So let's now turn to problem number 3, which is 2236. We have a y and we have an x-axis. This is x and this is y. And there is a charge, Q1, at these locations in x and y. Here is Q1, and there is here a charge Q2, and Q1 is positive, is 4 times 10 to the minus 9 Coulomb, and Q2 equals minus 6 times 10 to the minus 9 Coulomb. And you're being asked what is the electric field at the origin O. How is electric field defined? If I have a point A here and I have a point B here, and there is a charge plus Q here at point B, then the electric field is defined radially outwards from B pointing in the direction of A, because this is a positive charge. If this were a negative charge, it would be reversed. It would be pointing in the direction of B, so I call it E of A. And if the separation between them is R, then E of A, if I take the magnitude of it now, is the charge at location Q divided by 4 pi epsilon 0 R squared. And I already indicated the direction. The use of electric field, which by the way has as a unit Newton per Coulomb, is the following. If you were to place at location A a charge capital Q, then the force that this capital Q would experience would be simply the electric field at A times capital Q. So that's the reason why electric field is introduced. So let us now be specific here and first calculate the electric field due to this point Q1. Here is that electric field, E1, and I will decompose it into the x and into the y direction. So here is E1 in the y direction, and here we have E1 in the x direction. The separation from O to Q1 is 1 meter. The angle here I will call theta, so this is also theta, and this is also theta. What is the magnitude of E1? Let's do that first. The magnitude of E1, I put here bar so that it's magnitude, is simply this charge here, 4 times 10 to the minus 9, times 9 times 10 to the plus 9, because that's the 1 over 4 pi epsilon 0, divided by the distance squared, which is 1 squared, and so this is 36 newtons per Coulomb. What now is the x component? I now have to multiply by the cosine of theta, so E1 in the x direction then, multiplying by the cosine of this angle theta, would be minus 28.8 newtons per Coulomb. Why minus? Because it's pointing in the minus x direction. And what is E1? Y? Now I have to multiply by the sine of theta, and so I get minus 21.6 newtons per Coulomb. Why minus? Because clearly you can see it's pointing in the minus direction. Now I have to also calculate the electric field due to Q2. Q2 is negative, so it is pointing in the direction of Q2. I call this E2. It turns out it has only a component in the x direction. And so E2 you should be able to find now quite easily. It is already in the x direction, so I can already put an x here. That, if you put in the numbers, turns out to be 84.4 newtons per Coulomb. And you now have to calculate the net electric field. So you have to take E1 and E2, E net vectorially equals E1 plus E2, and I'm sure you can do that. Parallelogram. So this is the net electric field, and you should have no problems calculating both the magnitude as well as this angle, let's call it alpha, and I will leave you with that. That should not pose any more problems.